Okay, everyone, so let's go ahead and get rolling. So if you're just joining us, I opened up this poll everywhere question that's just, rate your question. That's how I'm going to collect questions today and try and address those questions that are being asked there. Certainly, it doesn't prohibit someone from miking in and asking me a question that way. I would encourage you to do that as well, if you do that. But if you see questions already on here that you're like, yeah, that's the one, go ahead and vote on it. And I will try and get to those questions as we move through this. So I am recording this. So, if you have something you're like, oh, I didn't understand what he was saying there, you can always recording and listen to that recording as well. Okay. Let me just, first of all, start off with, just a second, let me shut my door here. So let me first of all just start off with kind of some of the details, if you will, of the exam. So the exam will open up tomorrow morning at 8 o'clock. It will close at 6 p.m. Tomorrow night. You'll have 80 minutes to take it. You'll need to have equipped your computer with the Respondus Lockdown browser. If you haven't done so, please do so today. In fact, I give you a practice quiz to test if you've done that correctly. And I will give you 2 points extra credit if you take that practice test by the end of the day. So that would be 11:59 p.m. today. And that way, any potential issues that might come up are resolved before tomorrow, when we have, lots of people trying to get on and take the exam. And I know you'll have constrained schedules, so you might only have one time to really do that. Okay, so we want to avoid those complications before they even come. Okay, all right, so that's the details of the exam. 80 minutes, like I said, starts at 8 a.m., goes to 6 p.m. Log on at any point in time in Canvas and take it, and then we'll go from there. If you have issues, you're going to want to go ahead and contact me and let me know what issues you are having, and hopefully we can also get a hold of Respondus and their web support and go from there. Okay. All right, now, secondly, in terms of the format of the exam, obviously it's virtual, but the format of the exam will be very similar, if not identical, to what you see in the practice exam. So the exam study materials module, just below module 5, chapter 5 module in Canvas, has practice exam, and you'll want to look at that. That's the way the exam will look. There will be 2 essentially matching questions. Then there'll be a set of multiple true-false questions, and then finally 1 short answer question. The total point value of the exam is going to be worth 100 points. So you will be given PKs on the exam. You'll be given equations on the exam. Okay, so those things will all be available to you, so you don't have to have those stored in your memory. Okay. All right, so hopefully that deals with just kind of the logistics of the exam, and then let's go ahead and start addressing some of these questions here.
Are we allowed to have scratch paper and pencil in front of us?
Yeah, that's a great question. Sorry, I didn't think about that, and I'm glad you asked that question. Yes, you can do that. I know for students taking, a virtual exam or scratch paper, so go ahead.
Yeah, good luck. Good luck.
So I will say that right now someone's not muted. I can hear you talking, so you might want to look at that and make sure that you are muted. So, okay.
Nope. Yep. If you go into that email and then click on like
so
like that one email about week 5 reminders.
You'll probably want to.
But then he said he's also going to record it and post it later. So.
I am going to record this, and I am recording it. So just so you know, you're not muted. I don't know who it is. I can't see it, but if you're talking about. But anyway, make sure you're muted so not all of us hear what you're talking about. So, okay. All right. So let's go ahead and do this. I'm going to go ahead and turn off my video, and we'll move from there. It looks like someone's got something in the chat. Okay, there we go. All right, and let's just deal with, I'm going to start working through these questions, as many questions as I possibly can, and we'll see where we get by the end of this time together. So the first one says, can you go over how free energy relates to stability and how work can be done? Yes, I can. And so when we think about free energy and the stability of free energy and how or how a system is stable in relationship to that free energy change, and also how work can be done. When generally speaking, let's just say this: if the change in free energy is negative, right, and the more negative it is, the more stable we say that system will be. So if you were to think about it this way, this is a decent way to look at this. Okay, go ahead and draw this out. But if we were to think about even those free energy landscapes, right? Draw this out here. And there's lots of ways to think about this, but generally speaking, when we think about free energy changes, okay, and we can just put that we're applying reactants to products. This would be an okay way of doing this. But when we think about free energy changes, let me just draw one of these things here. This. A free energy change, even on something like this, okay, means that we're starting somewhere, let's say way up here, all right, and then the energy of the system is going to drop to its lowest point, okay? And when the free energy drops, okay, like that, as long as our initial conditions, right, are going to go towards product, okay, and that drop is going towards product, then what we see here is a negative free energy change, okay? And the well of that, right, is going to tell us about the stability of that system, okay? So for instance, once we reach this point, this equilibrium point, okay, we could think about that versus, let's say, something more shallow, okay? A system that would be maybe something more like this. Oh, that's not a very good drawing, but let me go ahead and try that again. Something like that, okay, where the system essentially starts here and goes to its lowest point. Well, right, that free energy change, the magnitude of that free energy change at the top here is not nearly as significant as the magnitude of the free energy change as the one at the bottom, okay? And so it's going to be easier for that system to come out of that equilibrium point, meaning that it would be less stable, okay, in that regard, okay? So that's kind of what we're thinking about here. Let me just put it this quantitatively, right? We would think about a system that has a negative delta G of, or a delta G of negative 25 versus a system that is equal to, right, negative, let's say 15, we'd say that this one, once it reaches its equilibrium value, is going to be more stable. Okay, it's going to have further dropped into, or it's going to go into a deeper well, okay, and therefore be more, okay. So I think that and it says, oh, how work can be done. Okay, so work can be done as the system progresses towards the free energy change. Okay, so when we start at an initial condition that is a higher free energy than what we would find at equilibrium, then that drop in free energy, that energy is coming out of the system, okay, and is going to go do work in the surroundings. Okay, and when we think about free energy, actually, it's just simply the energy within the system that can do work. Okay, right. So hopefully that addresses that question. I'm going to see some chat questions here. Let's see if these are related to this. So then the well at equilibrium is the KEQ? Yes. Yep. So that well will be the KEQ. Yep. So it's, and then we have this question. So is it the larger free energy change or the smaller total free energy that makes it more stable? It would be the larger free energy change that makes it more stable, the magnitude of it, okay? The bigger the magnitude, the more stable that particular system will be at equilibrium. I think let me go one step further in this, okay? I tried to use a graph that we're familiar with in this class, right? But let me go ahead and do something like this. You can also look at, and we'll be looking at unit diagrams too, okay? You could be thinking about a system that would, let's say, start here, and then there'd be a point here, okay? And you could chart out energy changes in a system that would look something like this, okay? In terms of a reaction coordinate, okay, well, what happens here is this: if we were to start here and we get to here, okay, then we're in this energy well. Well, it's going to take some pretty significant energy to get up this, or it's going to take some pretty significant energy to get up this, okay? So this would be a fairly stable position of our system. You know, another way to look at that would be to compare that, let's say, to this, okay, where we go from here to here and up like this. The energy it would take to get back over this hump or back over or up over that hump is going to be essentially less than the energy it would take to get in that original drawing, okay? So that the depth of that well is kind of what we mean by stability, okay? That's what I'm trying to relate this to, okay? Right, let me look at this. Negative free energy change drives towards progress. Yep. So negative free energy change will drive towards products. That's correct. And then how do we determine if delta G is positive or negative given a delta G prime not? Okay, so that's an entirely different question. So that's a great question. And let me try and address that. But let's go back here. So I'll try and remember that. Can we go over? Yep. So that's one of the questions we've got. So can we go over difference between standard and actual free energy? So let's do that, because that was a question in the chat as well. And then I'll come back up to this. How much about the properties of amino acids do we need to know for the exam? Okay, so let's do this delta G to delta G prime not. Okay, and the question in the chat was, well, how can I know? I think the question in the chat, let me look back at that. Let me address that too. How do we know if delta G is positive or negative given delta G prime not? Okay, all right, so let's talk a little bit about this and come back over here and go down to this, right? So we've got these two different concepts that we've talked about in this class, delta G prime not and delta G. Okay, now right off the bat, to handle that question that's in the chat, you couldn't know with any certainty whether actual free energy change is going to be negative or positive given just delta G prime not. You would have to have more information about the two systems, okay? Or you'd have to have more information about actual conditions to know if it's negative or positive, okay? And so let's think here about this, okay, and kind of go back over these concepts. I will say this: I did make a recording that I posted on these two concepts, actual free energy and standard free energy. It's about 25 to 30 minutes long, and it's found on Canvas. So you want to look at that if you're still really struggling at this, because I'll spend more time going over this, okay? But what we have here is this: when we think about these, either one of these values, okay, so we would have these two values reported for any particular reaction, right? So if we had, let's say, for instance, say X goes to Y, okay, we could say something like this, that we have a delta G prime not that is equal to negative 10 kilojoules per mole, okay? And then we could say that we have a delta G that is equal to, let's say, I don't know, I could pick any value really, but let's just say negative 5 kilojoules per mole. Okay, so it's less exergonic than standard free energy change, right? When we think about the difference between these two values here for our reaction, the main difference is where the reactions are starting, okay, where their initial conditions are. The reaction X goes to Y is going to end at its equilibrium value. Okay, that's the case. X goes to Y ends its reaction, okay, once it reaches equilibrium, okay? When you think about these free energy changes, okay, here, both of them have an ending point, okay? The same ending point, the KEQ. What makes them different in terms of the magnitude of how exergonic they are is where they start. That's the only real significant difference between the two, okay? So when we look at this one, and we say, well, it's standard free energy change, okay? We can say that we know the starting point with certainty because it is indeed standard conditions, meaning that this will start at 1-to-1 product to reactant ratio. Okay, that pen is not very good. Let me just say this starts, let's do this. This is more contrasting. So it starts at 1-to-1 product to reactant ratio. Always, standard conditions always starts there. Okay, now given that then this is going to be negative free energy change, that would mean that it's going to end at an equilibrium that has a larger amount of product than it does reactant. Okay, that's what the negative means. This will go toward product to reach equilibrium. Okay, that's what the negative sign means. Goes towards product, or it's exergonic, it's spontaneous, produces product to reach equilibrium. Okay, at its particular starting condition. So this one's going to start at 1-to-1, and then it's going to go towards product to reach equilibrium. Okay, which means this, given that we have this KEQ, right? We can say that, okay, right, that it's negative and it starts at 1-to-1, KEQ is greater than 1.0. Okay, and that would be derived from this equation, if you want to look, is equal to negative RT natural log KEQ. Okay, so the natural logarithm of a value above 1 is going to be a positive number, right? So then you have a positive number here above 1 times the negative sign on RT, and you're going to get negative delta G. So, just as a reminder, probably want to mute yourself. It sounds like some people are not muted. So if you haven't muted yourself, go ahead and do so. Okay. Right. So that's, standard for energy change. Starts at 1-to-1, okay, and then it's going to end, like all reactions are going to end at KEQ. From standard for energy change, we can predict the magnitude of KEQ, okay? In this case, like I said, it's going to be greater than 1, okay? Now, delta G, when we look at this, once again, okay, we can say negative. We would say that this goes towards product to reach equilibrium as well, because all spontaneous processes go towards product to reach equilibrium. Okay. Now we can't, from delta G, actual conditions, state the size of equilibrium. Okay, the equilibrium constant. We have to have standard for energy change to do that. Okay, but we can at least say if it's negative, that means it goes towards product to reach equilibrium. Okay. Now this one, and the big thing that we want to recognize here, right, this is going to start at Q, right? Product to reactant ratio at actual conditions. And for a biochemist, those actual conditions are going to be, something like what you would find in the cell or something along those lines. Okay. Right. So really, when we look at actual free energy change, we start to think about, Q relative to KEQ, right? Meaning our starting point relative to our ending point. Okay. And we can say this, that anytime we have a exergonic actual free energy change, we can say that Q is less than KEQ, smaller than KEQ, okay? And in this case, when we look at the conditions that I set up, right, 5 versus 10, we can say that because we have these two free energy changes relative to each other, we can say that actual free energy change, right, being less exergonic than standard free energy change, that the actual conditions are actually closer to equilibrium, meaning less work is going to be done under actual conditions than the conditions under standard conditions, okay? Meaning our starting point, okay, for our actual free energy change is closer to the equilibrium value than the starting point for the standard free energy change. And remember, the only difference between actual free energy change and standard free energy change is where they start, okay? Right. So, so anyway, right. So hopefully, you know, that kind of helps you. The question was, you know, what's the difference between standard and actual free energy change? And the main difference is where they start. Okay, both are going to be going to have their ending point at equilibrium constant. Now, like I said, there's this recording that I made earlier in the semester when we were addressing these concepts. If you haven't listened to that recording, please do. I go through this in a lot more detail. I go through it with the graph and everything. And hopefully that will clear up any potential confusion you have with regard to these types of questions, okay? All right. All right, so let's look at the chat and see what's going on. Where do you find that recording? I believe that, so I'm trying to think that, I think that I put it in an announcement, and I'm trying to remember if I linked it anywhere else. Let me make a note of this to make an announcement on Canvas showing you the link. Okay, so after I'm done with this, I'll make an announcement on Canvas showing where that link is. If you were to just pull up Canvas and look at the announcement page and go down it, you would find it. So, okay. So you won't, I would not, no, you won't need a calculator for these types of questions. The reason being that I'm not going to have you actually state the magnitude of the equilibrium constant. Okay, so you don't need, in fact, I won't let you use a calculator on these. Okay, so these would only be just relative terms. Okay, like is Q smaller than KEQ or is Q larger than KEQ, but not an actual value. So, or is Q equal to KEQ, that kind of thing. Okay, all right. If the standard, let me see here, I'm trying to do this. If the standard negative is negative, do we always assume actual conditions are negative? Is it that way in all the examples I've seen? It is that way in all the examples I've seen. No, good question, Molly. So you can have a standard free energy change that's negative and an actual free energy change that is positive. In that case, we would just say that Q is larger than the KEQ. So there's nothing prohibiting that from occurring, okay? When we get a metabolism, we'll find out that there's a lot of reactions in the cell that standard free energy change is either negative or positive, and the actual free energy change is zero, quite commonly. So, so that can happen as well. So, okay, all right. Yes, you can have scratch paper on these. Yeah. So, okay. Right. So let me go back now. Hopefully that addresses that set of questions. Let me go back here and let's look at this. How much about the properties of amino acids do we need to know for the exam? So I would expect you to be able to identify correctly the classification of each amino acid, right? So if I give you serine, I would expect you to know that that's a polar amino acid, right? If I were to give you lysine, that you would know that's a basic amino acid. I would also expect you, of course, with pH and pK and that kind of thing, to be able to predict protonation states and also then charge on side groups or side chains or R groups, and also, of course, in the alpha amino and alpha carboxyl group. So, okay. So that's what I would expect you to know for that, okay? All right, how does delta G relate to Q and KEQ? Okay, so that was, hopefully I addressed that question in that last one, right? So if we were to go back here, let me just do this one more time. Okay, so I did state this, delta G, standard free energy change is equal to negative RT natural log of Q. What I didn't do is state this, so I might as well state this. Actual free energy change is equal to, well, it's equal to, let me Let me give myself a little bit more room as I write this out. Delta G is equal to delta G prime naught plus RT natural log Q. Okay, where again Q is just your initial. Okay, now let me go ahead and delve a little bit deeper into this. Okay, and just to try and help people out with this. Let's say that we have this. We can rewrite this equation this way. Delta G prime naught is equal to this, to negative RT natural log KEQ, right? According to our equation over here, plus RT natural log Q, okay? And that's what delta G equals. All right, so let's do this. Let's envision a scenario, and I kind of mentioned this. Let's envision a scenario where our particular reaction starts at equilibrium. In other words, KEQ is equal to Q. Okay, well, in that case, if we were to do that, then, right, notice what we have here in this equation. We have then, right, if those two values are equal, then this part of our equation is going to be the same magnitude of this part of our equation. However, they have the opposite sign, right? This one has a negative sign on it, and this one has a positive sign in front of it. Okay, so if KEQ is equal to Q, then we would say that delta G is 0, right? Those two are going to cancel each other out. We have a delta G that's equal to 0 because our reaction started at equilibrium. And that means that the reaction has nowhere to go. It can't do work, okay? It has no free energy available in it, okay? So then when you start to think about actual free energy change, you start to change Q relative to KEQ, for instance, right? KEQ now is going to be greater than Q. In that case, then what happens is that the portion of the equation on the right gets larger, okay? Or I'm sorry, smaller than the portion on the right, okay? And you start to get negative free energy changes, okay? And you can go with the same thing. If Q becomes larger than KEQ, then you get positive free energy changes, okay? So there's other ways to do this, right? I've shown people the graphs, but you can certainly start to play around with these equations, okay, and start to plug values KEQ and Q into them, and just remember that your KEQ is essentially the ending point of that particular reaction, and Q is the starting point of that particular reaction. And you can start to see that, oh, okay, so if my Q is larger than or smaller than KEQ, what that means for delta G, is it negative or is it positive? Okay, so we can make rules for this. Q, anytime it's smaller than KEQ, means that we have an exergonic process. Okay, Q, anytime it's larger than KEQ, means that we have an endergonic process of positive delta G. So, okay, so there are other ways to do this, if you will. And certainly on that recording that I mentioned, you'll see me address this graphically, but you could also address it just quantitatively looking at these equations. So, okay. Right, looks like some of the chat is kind of filled up with some things. Okay, some people are leaving. That's great. If you have to leave, go for it. I'm recording this, so that's fine. If you give us a structure, well, we need to know which amino acid that is. Yes. Okay, so to just answer your question, yes, we will have to know that. Will amino acids always have a neutral charge when protonated and a negative charge when deprotonated? Okay, so let's address some of these questions with amino acids. Can you go over finding the charge in amino acids and side chains? Okay, so there's some questions filling up here in terms of the amino acids. So first of all, when you think about structure of amino acids, let's deal with this. First of all, I'm not going to have you draw any structures. That would hopefully be clear. Not all of you have tablets, nor are you going to be taking the exam on a tablet. You're going to be drawing these out, right? So this would be simply to recognize them, okay? Secondly, when we think about this, there's some questions on are side chains going to be neutral, or are they going to be, what charge are they going to have on them? Okay, when you look at the side chains. Oops, hit the wrong button there. Okay, there we go. And then how do we find charge of amino acid at pH and pK? So I can say this, I know exactly where this recording is. I did a video, about a 20-minute video on pH and pK for amino acids that's found just below LN04B on Echo 360. So go listen to that. It's going to be a great resource for you. Again, that's on Echo 360, just below LN04B, you'll find the PHPK video, okay? And I will again send out an announcement about the video about delta G prime naught and delta G, okay, which we've spent some time thinking about already, okay? But let me just quickly address some things with pH, with PK, with amino acids, and just strategies in terms of how do we determine the protonation state really of any functional group, okay? First of all, let's do this, okay? Anytime we look at an amino acid, there are really only two groups that you would find on an amino acid, okay? And that is going to be a carboxyl group, which if I were to draw it in a protonated form is going to be like this. So this would be a protonated form of a carboxyl group. And then we'd have a deprotonated form of a carboxyl group that would be over here, okay? So real quickly, let's just think about this. Let me draw out the amino acid aspartate, okay? So aspartate will have, of course, actually, I started that in the wrong direction, okay? Aspartate is going to have the alpha carboxyl group. Okay, and I'm just going to go ahead and draw it in a deprotonated form, but that's the alpha carboxyl group. pK of that would equal, I don't know, it would equal something around 2. Okay, I can't remember exactly what the pK1 of aspartate is, but that's a carboxyl group, an alpha carboxyl group. Now, at the same time, if I were to draw the side chain of aspartate, the side chain also has a carboxyl group on it that will also have a negative charge. Okay. So when I say that we're looking at functional groups in amino acids, I mean that we have carboxyl groups. Certainly all amino acids have the alpha carboxyl group. But then there are some side chains, like aspartate, the one that we're looking at here, that will also have on its side chain a carboxyl group that will have the same type of chemistry that's shown for the alpha carboxyl group, okay? Right, so remember, just when we say carboxyl group, that just simply means, a COOH, okay? And those can be found, alpha carboxyl group or on side chains. Right? Now, when we then go on further into this, we can say also that another type of group that you would find on an amino acid side chain would be this, an alpha amino group, RNH3 plus in its protonated form, and RNH2 in its deprotonated form, neutral charge. Okay, so coming back to our amino acid here, aspartate, we could put this as its alpha amino group, right? And then of course it has a hydrogen. Okay, so there are the 4 different things that are connected to the alpha carbon: an alpha amino group in its protonated form, side chain, which has a carboxyl group on it, and then an alpha carboxyl group, which in this case is deprotonated, okay? And all amino acids are going to have, of course, the alpha amino group and alpha carboxyl group. Now, let's do this though. Okay, let's go further into this and let's draw the amino acid lysine, right? So this is aspartate, by the way. Let's draw the amino acid lysine. And again, it was going to have a carboxyl group. We'll go ahead and draw it as deprotonated form. Okay, and it is going to again have an alpha amino group, just like aspartate. I'll draw it in its protonated form. But at the same time, lysine also has on its side chain an amino group, okay, which has a positive charge in its protonated form, okay, right? And then we have the hydrogen here, okay? So when we talk about, and you think about, doing these types of problems, okay, in determining charge on an amino acid at any given pH, given pKs, it's very important to just remember that, okay, we have these 2 different types of groups that can form a protonated form and a deprotonated form, right? So I think one of the questions in the chat was, will, you know, I think it's said something along the lines, will they always be neutral when protonated, or the side chains will always be neutral when protonated and you know, have a negative charge when they're deprotonated, or something to that effect. And the question is, no, you can't say an always, you know, type of a statement with side chains, okay? Because side chains can have either an amino group on them, or they can have a carboxyl group on them. And if a carboxyl group is deprotonated, then it'll have a negative charge. If an amino group is deprotonated, it will have a neutral charge. If it has, if the carboxyl group on the side chain is protonated, then it would be neutral. If it's an amino group on the side chain, then it would be positive, right, protonated. So you can't make a rule like that. You would have to know, okay, which side chains have like an amino group on them, which side chains have a carboxyl group on them. How can I determine when they're protonated and when they're deprotonated based off of pH and pK? Okay, so those are things to keep in mind as we go through this. Now, I will say this, right? When you think about, generally speaking, the basic side chains, we can say that if those are protonated, they're going to be positively charged, okay? That would be lysine, arginine, and histidine. Now, when you look at histidine and arginine, their structures don't really have a classic amino group that looks just like this, but they do have a nitrogen that has 4 bonds around it, okay? And that the nitrogen with 4 bonds around it would then have a positive charge, so, okay? And then if it deprotonates, it would be neutral, and it won't deprotonate until that particular functional group has the pH has exceeded the pK, right? When the pH exceeds the pK, then we can say that that functional group is deprotonated. And in the case of the basic side chains, that would be neutral, okay? Now, acidic side chains, right? Those are going to have negative charge when they're deprotonated, because the 2 acidic side chains are glutamate and aspartate, right? And when they, and the glutamate and aspartate have carboxyl groups on their side chain, and therefore if they're deprotonated, then they'll have a negative charge, and if they're protonated, they'll be neutral, okay? And again, they'd be deprotonated when the pH exceeds the pK, okay? So those are things to kind of keep in mind, and just in terms of general trends that we see there, so, okay? All right, let's come back to the chat. Looks like some things happened here in the chat. Let me go up. I have a hard time scrolling this. Okay, is there a way structurally to tell if an amino acid is polar versus non-polar versus basic? Let me get to that question here in just a second. Also confused on question 18, how we can determine the rate of formation. So I'm not following that part of the chat. The amino groups on the R groups and the alpha group, alpha amino groups don't necessarily have the same pH, which they get deprotonated at, right? That's correct, right? So coming to this question, that is correct. What you would have there, you'd have to look at the difference between PKR and PK2. PK2s are generally going to be somewhere around 9. The PKRs for the basic side chains are, you know, 6 for histidine, it's 10.53 for lysine, and it's 12.48 for arginine, okay, compared to their PK2s, which are like around 9. And then you could say the same thing about alpha carboxyl group and the side chains on aspartate and glutamate. Aspartate's PKR is 3.65, and for glutamate is 4.25, and the PK1s of those would be somewhere around 2. Okay, so someone answered that question. Now coming back to this up here, and then I'll get, is there a way to structurally tell, or was it? Is there a way to structurally tell if it is polar versus non-polar versus basic? Yes. So generally speaking, when we think about polar side chains, let me just draw something out here. This would be serine side chain. Polar side chains are going to have some group, like a hydroxyl group on them, that will have, you know, an atom like an oxygen that's very electronegative bound to, let's say, a hydrogen, which is not so electronegative, and that will make a polar, right, type group, okay, or make a dipole or a dipole moment, right? So we look for those types of things that can participate in hydrogen bonding, okay, and you know, difference in electronegativity, like nitrogen bound to hydrogen, okay, and that kind of thing. Non-polar side chains won't have that. They'll generally be just aliphatic, okay, so meaning that a non-polar side chain like this one, valine, okay, it's got methyl groups on it. right? And then, you know, that CH group on it, that is not going to be non-polar hydrocarbon chain, right? It doesn't have any of the electronegative atoms like oxygen and nitrogen on it that will make for a dipole moment. And then when you think about acidic and basic, really what you want to be thinking about there is, you know, do the side chains have PKRs? Okay. And if they have PKRs, then we can start to classify them as acidic and basic, generally speaking. The PKRs of the two acidic ones are really low, and for the most part, the PKRs of the basic ones are pretty high. Okay. So yeah, you can, and structurally speaking, right, again, you're looking for like an amino group or a carboxyl group in those cases for like an acidic side chain, a carboxyl group, and an amino group for a basic one. So, okay, let me check this out and go back to here. Okay, so we've dealt with these ones, these top ones. Let's move to this one. How do I know where the phi and psi angles are on an amino acid? Redress. Okay, so let's do that real quickly. Come here, phi and psi angles. Let's check this out. And let me go ahead and draw for us a peptide. Okay, so we'll start here. And there's the peptide bond. I'll put boxes around the peptide bond here in a moment.
If we were given a problem where we have to look at pH to determine like protonation versus deprotonated on like any of the side chains, would we be given the pK of those?
Yep. Yep. Yeah. So I would definitely, so so if you look at the practice exam, at the top of the practice exam is essentially what you're going to get on this exam. And that will give you PK1s, PK2s, and PKRs. Yep. So, okay. All right, so coming back to this, let's look at this here. And let me just draw the end of this. Okay. All right, so let me just highlight for us here. Here would be a peptide bond here. Okay, and when we look at that peptide bond, and here would be another peptide bond here. Okay, and then we'd have, let's do just a real simple amino acid, glycine. And of course, coming off that would be the proton. Okay, so the question is, well, how do I know what the phi and psi angles are? Okay, so the peptide bonds, remember that bond there, let me just go ahead and highlight it. That bond right there, that bond right there have double bond characteristics, which means they don't rotate really. Okay, you have cis and trans, and that's about it for those. Okay, however, these bonds here, right there and right there, those are single bonds, and those would be right to this alpha carbon. So this is an alpha carbon. Okay, and the question is, well, how do I know, yeah, right, which of those then represent phi and psi angles, right? So because they're single bonds, they can rotate, and that means they will have then dihedral angles associated with them. And with the dihedral angles, then we label what, you know, the name of those angles, right? Phi and psi, right? And, you know, the best way to remember this, at least in my mind, this is how I remember it, is this, okay? And that is that when I look at this bond connecting the C and the N, okay, versus this bond connecting the C to the C here, how I remember this is that I say, well, this angle of rotation is going to be denoted as psi. And how I remember that is because it's two C's bonded to each other, and phonetically psi and C sound similar. Okay. And then the other one by convention then must be phi, which phonetically doesn't sound anything like N and C, but that's how I remember this. The other one has to be phi. So that's how I remember this, and hopefully that addresses your question, right? The question was, how do we know phi and psi angles are where they are in an amino acid. They're always going to be, the defiance angles are always just to the right and just to the left of the alpha carbon. Okay, if you draw it the way I did, and then to remember it, you just have to figure out, okay, well, which single bond is being formed here? Is it a CC bond? That's a psi angle. If it's a NC bond, then it's phi. Okay. All right. Got some chat questions. Let's look at those. Does this count for extra credit weekly hour? Yes. If you, especially, so the great question, I didn't address that. Please go ahead and respond to the poll everywhere question. That's how I'll take your attendance here. So, okay. If side chain does not have a PKR, can we assume that they do not have a charge? Yes. Yes, you can. Okay. Can we go over pitch for an alpha helix? Yes, we can go over pitch. The main driver of tertiary structural formation. Okay, so we got about a couple more minutes here. Let's try and address a couple more of these questions. Can we go over pitch for an alpha helix? Let's do that first. And that means I'm going to have to draw something here of an alpha helix, and it's going to be really poorly done. But I'm going to go ahead and right. So if I were to look at an alpha helix and think about an alpha helix, remember this is going to be this curly Q. It's going to look something like that. Okay. And when we think about pitch can be just very simply this. If we've gone one turn, okay, up. Let me just kind of do this. We're going up, 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 around, and up, right? We've gone one complete turn here. The distance separating that atom there and that atom there is the pitch. And the pitch is 5.4 angstroms, where angstrom is just a really small unit of measure, 0.1 nanometers per turn. Okay, so if you were to think about like a helical staircase has a pitch, right? You step on the step, your first step, and you go up the staircase, one full revolution of the staircase, and you are going to be X number of feet off the ground by the time you get that full revolution. Let's say it's 3 feet. You get a pretty tight staircase, right? We'd say that the pitch of that staircase is 3 feet, okay, because you traveled upwards 3 feet when you went around this. So it's the same thing for a helix. It's just that the unit of measure is really, really small. It's 5.4 angstrom. Okay. Right. All right, so is there any way you can clarify different PKs like the graph of the practice exam, specifically 51 through 55, and how and why to which are correct? I don't have the practice exam up. Is there any way you can clarify different PKs like on the graph of the practice exam? I have to pull the practice exam up to see what that question means. Let me do that real quick. See if I can't find it real quickly. Okay, there we are. Let's pull this up. Okay, there we go. Great, we're in business. Oh, okay, yeah. So the question is in regards to those PKs, right? So, yeah, so remember, let me just circle these. PK1 is always going to be a reference to the PK of the alpha carboxyl group, right? PK2 is always going to be a reference to the alpha amino group, and then PKR is always going to be a reference to the side chain or the R group. Okay, so let's come back to what I've been drawing here. I can't remember which one I was working on. This one. Okay, so let's come back here. Okay, so we have an amino acid here. Right? The alpha carboxyl group is this one, and we give that, we will always denote the PK for that alpha carboxyl group. Okay, when we look at this one, we will always denote the alpha amino group as PK2. Okay, and then finally, for the side chain, will always be PKL. Right, so when you think about this amino acid, what we call triprotic. And because it's triprotic, it has 3 different PKs, and so we have to find some way to label the PKs. So we will, by convention, say PK1 is alpha carboxyl, PK2 is alpha, and PKR is the side chain. Okay. Good. All right. So let me do this. Let's try and address 1 or 2 more of these questions. See if I can't get through 1 or 2, and then if you have to go, by all means, go. Okay. I'll hang out for just a little bit longer, try and address a couple more of these questions and go from there. Okay. Please go over Fines angles. I did. Also, we can start the exam at any time before it closes at 6 p.m. So we should start before 4. Yes, yes. Don't run your time into past 6 o'clock. Okay. So yeah, if you want to take the full 80 minutes to take the exam, right, then you're going to want to start what that would be, at the very latest at 4:40. I would not start at 4:40 though, because you'll probably get cut off, right? It's going to take you a little bit of time to get through things. All right, we've talked about these. We'll have to know how to make a free energy diagram. It is not on the study guide. You would have to know how to interpret a free energy diagram, sort of similar to what we did in some of the quizzes. Okay, you're not going to know how to make one. You don't have to make one because I'm not going to ask you to draw anything on a virtual exam. So, okay. Given a full protein, do we need to know the structure of each amino acid to determine charge? Yes. Yep. So you'd have to know at the very minimum, the side chain structures and which one are going to the overall charge. So yes, you have to know that. We'll go over how to make a helical wheel diagram. Okay, great. Let's go over conditions that alpha helix would form or break. Okay, right. So those last 2 questions. Let me just do this. Can you go over conditions that alpha helix would form or break? And can you go over how to make a helical wheel diagram? So I posted a recording of worksheet 3 today on Canvas. So it might be a good idea to go ahead and look at that for those questions because we're really out of time. And I show you how to make the helical wheel diagram, and we spent almost that entire time thinking about what causes an alpha helix to form or to break. Okay, generally speaking, when we think about an alpha helix forming, we need to be thinking about what types of side chain interactions are going to happen between amino acids that are 3 and 4 apart from one another. Okay, so that's what you need to think about. If they're repulsive, not favorable, then you think that the alpha helix is going to fall apart. Okay. Right. So let me do this. I think that, okay, so it looks like people will indicate what alpha carbon is on the exam. If I were to put a drawing of a peptide, it would be obvious, hopefully, given what you've done, where the alpha carbon is. Okay, you might want to look at those drawings but hopefully you would be able to pick it out based off of what we've done in class. So, okay, but to this, it is time to go ahead and stop. I'm a little bit over. I will hang out until 1 o'clock with people that have other questions. But I'm going to go ahead and stop the recording now. And hopefully this was helpful to you. Make sure you check out some of those other videos I referenced as well. And good luck on the exam tomorrow. I will see you next week, and because we'll start synchronous sessions again on Tuesday of next week. Okay. All right. Take care, everyone. And again, I'll hang out while people exit. Okay. All right.
Thank you.
Absolutely.